All right, we're back. The thing says we're live. Hey guys, what's going on? Memes here. We're now down for session two. Well, technically this is three. Second of our day. And we're going to continue working on our units project. We got some correspondence from Rick a little bit earlier, and got to take a look at some Steam tables. So I don't want to spend too much time on this just because it's again, this is not a PhD thesis or anything. This is literally we got like I literally have like a week. I literally have about a week, less than a week and a half to put this all together, go through the editing and everything, and then finally make a community post. Not next week, but after the holiday weekend. Because next Friday is the 4th of July, I believe. And okay, so let's first do the dangerous thing. Let's share our entire screen. All right, let's go over here. Steam tables temperature. All right. Excuse me. Let's go to the history. History of steam tables and temperature. All right. 1840s. Okay, so that's within the realm. Oh, and ISD has an article. Let's see. Early history of steam power and steam tables. All right. All right, 22 megapascals, blah, 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 blah. Control F4. No, there's too many fours. Let's see. For the see? No. All right. Oh, it's only 7 pages. Okay, that's not bad. Let's see. Let me actually skim through this. Where are we? Let's see. Need for standard representation. Steam power. All right. About 2,000 years ago. Figure showing a workable steam table. Reaction turbine was included in a book by Hero of Alexandria. Wow. In which steam or hot gas could be used to do mechanical work. Wow. Let's see. Here was the very first steam table in the 1840s. The original with some assistance from a young William Thompson, who later became Lord Kelvin. Begin international standardization. A set of skeleton tables consisted of a rectangular grid of temperatures and pressures with values of specific volume, enthalpy, not entropy. I think that's inverse entropy. Hold on, let's 1 over entropy. And hold on. Enthalpy. There we go. That is interesting. Enthalpy is basically energy, because that's mass times length divided by time, aka mass times c squared in its maximal form, aka the joule. That is interesting. Oh, enthalpy is typically, I think, what they use for temperature there. Okay. Because it has the same dimensions. Okay. Oh, let me just bring up an email that I have here. Sorry. So much correspondence, so little time. All right. Well, depending on your perspective, maybe there's a lot of time. Maybe that could tell us something. All right. CNC comment. All right. Silence Asylum is doing his little thingy. Okay, let's see. Hold on. Where is this? When steam enters renew ice, water, and steam, as the steam, the chart, in the days when studied ice, water, and steam a lot. Well, I think that's where they got the triple point of water, which is a very fascinating thing. Water under a frozen lake in nature. Okay, they're finding fascinating things in like the Arctic and stuff now. It's like, oh, under all this ice, oh, there seems to be water. There seems to be ecosystems. How can that be? Fascinating. All right, so let's see. Format and table 1. All right, so we should have some figures here. Ah, here we go. All right. Oh, they're not showing 4 degrees Celsius. Why might that be? I have no idea. Okay. Okay, at 0.01 degrees Celsius, we got our pressure, and that's in megapascals. Pascal is the unit of pressure, and mega means million. Percent volume liter. Oh, there, that's very close to 1 liter. Oh, look. At 5, it's 1. I wonder what happens at around 4-ish degrees Kelvin at the appropriate thing. It might actually equal precisely 1 liter. That's really cool. Okay, the enthalpy, so aka kilograms, kilojoules per kilogram. Okay, for some reason there's nothing there. Well, I mean, it seems to be very little temperature. Okay, 2,500. All right, so is that? Oh, okay, entropy, because I was going to say there's an S there, and then I didn't read that part. Okay, so the entropy, kilojoules divided by kilograms per Kelvin. Oh, this would be a little bit of the same thing popping on over there. Huh. Very neat. Very cool. All right, so we got thermal conductivity, viscosity, got some cool stuff. Ah, okay, I think, here we go. The regions of the IAPWS IF97 standard for thermodynamic properties of water and steam for industrial use. Huh. Okay, this is temperature divided by Kelvin. Okay, so basically, I believe this is the ideal gas law that they believe, and this is kind of how they figured out that basically the minimum of temperature would be negative 273.15. Why is it not negative, or they're just using an absolute scale? I think this is an absolute scale. That's what makes sense to me. Okay, so I believe this is solid, liquid, gas. Oh! Okay, that's 4. I think that's 4 degrees Celsius. Huh. Standard pressure and temperature. I think that's standard temperature pressure. Let's read. Okay. Let's see. It remained the standard of power industry for at least 20 years. So, well, it was at least used by people that were trying to make money. So it's probably something that they're trying to figure out. All right. Final question to be addressed is when the appropriate use of the industrial formulation as opposed to formulation for general and scientific use. Okay, so they're using when it's preferred. In the steam power industry, they used that one. It makes sense to use for calculations all facets of power industry, where computing time is at a premium. The calculation of water properties consumes most of that time. Oh. Okay, so there was a more detailed and then a so-called quick and dirty method, it sounds like. First is the migration from printed tables to computer software. All right, computer generated properties, blah, blah, blah. Increased use of computers. Fortran language. Okay. Oh, wow, this is an OG thing. Sample screen from Steam Tables database. Ooh. Ooh. Okay. 360. I mean, that's just temperature, but I don't know. It's if being a human observer like myself, I'm just like, oh, that sounds like pi to me. All right, so the density. Okay, so okay, then like one is temperature. That's in Kelvin. Okay, so at 300. Oh, okay, okay. Those are just the rows. Noob. All right, so this is the actual thing. Those are just the cell numbers. Okay, don't mind anything I'm saying. All right, so at about 300 degrees Kelvin, so that's typically around room temperature-ish. I think, what is it, 272-ish, 2.5 or something like that is room temperature. That's that's pretty darn close to 1 liter is approximately 1 kilogram divided by meters cubed. I mean, that's probably why they originally based the kilogram on a deciliter of water. Huh. Very interesting. Because it's almost 1,000 kilograms. All right. Let's see. So the density there. All right. Enthalpy. Oh, that's very neat. For viscosity and thermal conductivity, aqueous solutions. All right, all right. So, hey, Jedi and Morgan. Zotra, let's see. Yes, yes, yes. Oh, I think that says Go Memes, but I can see that's GA, which maybe it's Gauss's constant as well. When in doubt, Gaussian ain't a bad way to be. All right. Create a hologram placed in a spinning zoetrope and flash strobe light to create an animation of an object. Zoetrope. I feel like I've heard that before. Zoetrope. Oh, yeah, I think Henry Segerman, his collaborators have stuff like that for, hold on, figure 8 knot. Hold on. Henry Segerman. Matt Parker, who can't make it to Henry Segerman's exhibit. Okay, let's see. Reddit math. Okay, so let's just take one. Oh, I remember this. I remember this. They're walking through. Okay, no, actually, this is a different one. Okay, they got a globe. Oh, that is cool. I think if I spun that, I would get very dizzy, though. So, all right, cool. Very neat. Spinning and a strobe light. Yeah, it's. Yeah, yeah. No, I mean that's gonna look like a pretty neat projection. So, all right. I digress. Let's go. Let's go back to our history. All right. Now we're Boltzmann's constant. Okay, let's get to our other constants here. So I apologize. There's going to be a section for proposed follow-up work that I can do next year or in the future. So don't worry. Well, I'm going to need to have to do the caveat. This is not the history of yours is extremely deep and very vast, and this computational essay is just a mere glance at some of the history and should not be considered an exhaustive study on the topic because you can literally write books and books and books about this. It's a fascinating thing. I know. Was it? I was talking with Bill Manuel a little bit earlier. He's actually a meteorologist. He uh, he worked. Was it for GM or Ford? I think it was Ford. And he was in some of their labs, and he designed some things that it's like, all right, you could do all this fancy stuff, or we could do it the real way. To being hands on and actually doing stuff, I feel is very useful. Like I think a lot of physicists often or musicians, because if you're a musician, you're playing a piano, a violin, you're getting a sense for vibration, oscillation. You touch a thing, it does some stuff, and I think that helps our intuition. Okay, so let's go back to our SI definition. So we've done the meter, the second, the kilogram, the ampere, the Kelvin. All right, let's get into the mole. Now, full disclosure, there are several people I've talked to that are like, listen, this is just a number. This seems like a very human convention. And as a wise man once said, we can count. I'm going to assume we can count, and I'm going to argue that we don't necessarily need this. I say that, and again, I'm going to talk out of both sides of my mouth because hypothetically, again, this isn't really for this, but hypothetically, if we were to assume that, let's see, we take solve for x kilograms, we divide by Planck mass, and we set that equal to the meters over Planck length on the minimum, and we square that whole dang thing. It's going to give us a number. Gives us a ginormous number here. That's in kilograms because that's what we were solving for. So long story short is, it ends up. So this is actually 1.5 here because it's, yes, extra digits. Okay. So again, the claimed mass bank, according to a totally crazy conjecture of universe, is that much. The one thing that makes me suspect that maybe Avogadro's number, and again, this is absolutely nuts for a calculation, might actually have to do with something is if you take this total mass or mass bank of universe, that's a ginormous number. I don't know what to do with it. Let's divide it by Avogadro's number. Why? Because we can. Avogadro's number. We get this number here. And again, it's like 1.38 times 10 to the 38 kilograms. I don't know what that is. However, Wolfram Alpha has some ideas. 10 to the 38 kilograms is approximately the mass of a tipular globular cluster. Globular cluster. Aren't those like those star nurseries that kind of eventually generate a bunch of stars, and eventually you get some of those coming together, and you get galaxies as we know it? Just a coincidence. I digress. But, it's a 3D holographic image on while spinning a strobe light. This is the answer I need for all my searches and solutions. I mean, I would like to know more if you have something that could direct me, or my email should be on my page. Happy to take a look at things. I've got a big list of things to do, and people have discovered fascinating things. I know Nerdy's got some code that I really need to play with. I'm just looking at it, I'm like, why is Euler's number there? He's like, oh, I didn't even notice that. That just kind of came out. It's like, And some of the correspondence with Rick has just led to, oh my God, I do some quick calculations, assuming what Rick has kind of shared with me in some of the Wolfram model, and I just look at it, I'm like, no, we'll get to that at a later point when it's. But yeah, no, Morgan, if you got something, shoot me an email. So, all right, let's get back to it. All right, where are we? Redefining the mole. Mole. Okay, in suburban Maryland, on the third floor of the Advanced Chemical and Sciences Laboratory at the NIST, Bob Vluck and Savalis Rab are explaining how they helped him to redefine the mole. That mammoth concept we learned in high school science. What is that? That's 10 to the 23 number. It's like, what? Okay. So let's try to analyze this, and let's see if we can't give the mole some grounding, because I'm actually curious about this. So, all right. So mostly this means using abstract symbols and numbers dancing along in a long equation that Vok obviously thinks is beautiful. You can tell because he enthusiastically writes each detail out on the whiteboard for some lab visitors. Every so often, Rab provides suggestions or tells a joke and sort of eggs Vok on. It's clear they're having a good time and could do this kind of annotation and explanation all day. Hey, at least they like their jobs. I mean, power to them. Okay. So that's Avogadro's constant. All right. 8V, so that looks like 8 volume, and that looks like, is that the Bohr radius to the third? Okay, then times mole divided by the M sphere equals that. Okay, so feel free to trust. Let's verify. NIST mole. Not molecular weight, we just want the mole. Okay, let's just do this. All right. Da-da-da. Search. Mole. They literally just have a mole. Huh. They don't have it on the physical constants page. That's interesting. All right. I digress. All right. After these questions, they add more. Okay. So, okay, we're going to need, I think that's Rydberg's constant. After these equations, they add more. All right, so H is Planck's okay, is this how to define the kilogram? Okay, I think this makes sense then, or at least, maybe. Okay, so that looks like the fine structure constant squared. That's alpha squared times an m, and then is that the mass of the electron times c? Let's try this. Okay, hold on, let me go over here. We'll put this here. All right. So let's go to Wolfram alpha. All right, so let's do the, all right. Fine structure constant squared. Let's do the mass of electron, or electron mass. Electron mass. And speed of light, let's see what we got there. Multiplication. Okay, so that gives us momentum. Groovy. Oh, look, 12 times the momentum of visible light. Cool. All right. I think that's Rydberg's constant. Hold on. Rydberg's constant. Yep. All right. Okay, so let's put two of those guys down in the basement. Do Rydberg's constants, because two of them equals... What is Rydberg's constant anyway? Spectroscopic wave number. Wow, we got a lot of digits for... Wow, that's very precise. Spectroscopy is very useful. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that's yeah, that's a really cool number. What is 1 over it? I'm just curious. All right. Okay. How about the limit of microscope's resolution? Okay, so we got 2 of those, and then I think that's Avogadro's number. Avogadro's number. Okay, so that gives us angular momentum. That is not equal to h. That is not equal to h at all. Rydberg's constant affinity. Let's just do hydrogen Rydberg constant. Maybe that will make it up. No, that doesn't really make it better. So we got alpha squared, mass of the electron, C. You got two Rydberg's constants, Avogadro's. Oh, it's supposed to give us. Hold on. What dimension? We're in angular. We are in angular momentum, but I'm. Wait a second. Okay. We have Boltzmann's constant, which is redefined. The Faraday constant. Why? Huh. Let me throw the protons. No, that's only going to be like 3 orders of magnitude. Let me make sure I have Avogadro. Make sure I'm using the right thing. Yeah, it's Avogadro. Oh, did I use Avogadro's constant? I mean, that doesn't seem to be helping. Unless that's the alpha particle squared? No. Hold on, let's actually read. Why does it give us... Hold on, does it give us anything? Okay, it appears there, redefining the mole, blah, blah, blah. Let's see. Okay, go back. Okay, to fully grasp the new definition of the mole, you must embrace these long equations which show how measurement connects fundamental constants of the universe, such as the speed of light, the vacuum, the amount of charge, and electron. Oh! Is that supposed to be the charge of the electron? Or is that just a mole? Oh, I think that's a mole. I did that wrong. Okay, hold on. Okay. So let's... Okay. Oh, because those are really big numbers. Okay. So Electra... Okay, so let's do this. Mole. Elementary charge. Okay, we're at least getting a little closer. Maybe that C was supposed to be for charge. Nope. Okay, Wikipedia. Help. Help, you're my only hope. Units, mole. Alright. The mole is the unit of measure, the base unit in the international system. Yeah, so that base quantity is number of elementary entities of a substance. One mole is an aggregate of exactly times 10 to the 23, which is basically 3 orders of magnitudes of Avogadro's number. Which, I mean, isn't that how it's defined? Yeah, it's Avogadro's number. Yeah. Okay, so 1 mole. Ions, pairs, particles. Number of particles of the mole is the Avogadro number. And the numerical value of the Avogadro constant expressed in moles to the negative 1. All right. The relationship between the mole, Avogadro's number, and Avogadro constant can be expressed in the following equation. 1 mole equals Avogadro's number over Avogadro's constant. I mean, hold on. Avogadro number. Got that to like 10 digits, I think. Yep, we got to 10. All right. So let's just grab this real quick. All right, 6 times 10 to the 23. Yeah, it's just inverse amount. Yeah, it's just 1 mole. Yeah, that number divided by that, okay. But how do we justify it? The current SI value of the mole is based on the historical definition of mole as the amount of stuff corresponds to the number of atoms in 12 grams of carbon-12. Okay. So we made the molar mass of a compound, how we get the atomic mass unit. There's molecular mass of the formula compound expressed in Daltons, aka the atomic mass unit. A couple of slightly tweaked versions, the numerical is now only approximate, but may still be assumed with high accuracy because they kind of redefined the AMU, which seemed to irritate some folks. But they're like, oh, for most purposes, it should be the exact same. I'm like, or at least it doesn't deviate until, I don't know, it's 8th to 10th digit, something like that. So for almost all instances, for humans, it should be okay. Unless you care about those last couple of significant digits, which some folks do. Okay. Mole is widely used in chemistry as a convenient way to express amounts of reactants. And for example, the chemical equation 2H2 plus 2O2 equals 2H2O can be interpreted to mean that each 2 grams, okay, so we can do water. All right, as a set. Concept of mole is similar to words like pair, dozen, these describing identical objects. Usually daunting as for the mole, number of objects a second by it's difficult to comprehend. So, okay, hold on. I'm going back to that other. Where was that? Over here. Okay. So if we know basically, that's the wrong dimensions. I'm just going to do, we still need C in there, speed of light. In a vacuum. Okay, so let's take the mole out. Okay, so we got 2 alpha in there. Hold on, God. Alpha squared. Okay. So we need a mass because we need to get into angular momentum or joule seconds. So electron mass. Alpha squared electron mass. What was the other thing they had there? Okay, so alpha squared, elementary charge, C, 2, and that's Avogadro's constant because it's, no, it's Avogadro's number. Okay, we should be in the, we're in joule seconds, we're in the ballpark. All right, so we're gonna do this. We need to solve for X. Okay, so we're going to solve for X to find out what the heck I'm missing. Equals Planck's constant. I think this is too many terms. Yep, too many terms. All right, so let's go back. And let's take... Let's just figure out what we need. Okay, so let's that by Planck's constant. So we should be in the same dimensions. Constant. Okay, so I suspect if I swap this around, we're going to get Avogadro's number. Yep. Okay. The total number of things in the mole. Okay, so 622,140, and it's rounding there to 8. Okay. So, but, oh, okay, so that's, what did I do? No, that's Avogadro's constant. Okay, so that's Avogadro's constant, and then that should be Avogadro's number. Okay. So Avogadro constant. Okay, so Avogadro constant in the denominator. And Avogadro's number in the numerator. Avogadro's. I mean, this is kind of seeming like a loopy definition. Avogadro's number. Okay, and then we should get Planck's constant. Okay, we've got a mount there. It's the right magnitude. I think that's a 7 in the next digit. It's rounding a little bit there. Hold on, let me see. Does that help? Nope. I mean, that doesn't really make sense. Do I just put it here twice? Number? Because it's basically just going to cancel it out. Okay, yeah, it gives us Planck's constant. I mean, it's just 1. Why? Oh, it's supposed to be a mole. That's why. All right, so that's Avogadro's constant. That gives us a mount, and if we divide by... Oh, I'm dumb. All right. So it's giving us a mole, Avogadro. Okay. I'm seeing the proportionality, but I don't really understand. Because, I mean, like, if we just take the mole out, take out Avogadro's constant, it's giving us Planck's constant. Like, that's it. Those are just reference ones. Okay, maybe that makes sense, because, hey, I'm making a big deal about reference ones, so, okay. Actually, maybe this could be part of the argument for it's like, all right, if you want this to actually make sense, you need to divide it by kilograms. Otherwise, the dimensions won't balance on each side. I'm like, well, how can you just divide by the reference? I don't know. NIST and CODATA seem to be doing, or at least NIST seems to be doing that for the mole. You've got a thing divided. Okay, it's mole divided by Avogadro's constant. So let's just do that. Mole divided by Avogadro's constant. Gives us square moles. I think. Divide. I might just need to... Do I need to take the geometric mean? Okay. Well, if you just multiply them, yeah, it gives you the number. I don't really understand. Okay, I'm just going to continue. I'm sorry. Well, I'll deal with that with a bunch of other smart folks that actually have PhDs and have studied this a lot more than I have later. Okay, hey, welcome back, Dan. I mean, Morgan, I suspect that. I mean, that sounds very right. Yeah, send me an email. I'm happy to look at a whole bunch of ideas. I've interviewed a plethora of different crazy folks. Some who, personally, I think may actually be sufficiently crazy. Hi, Dan. That's the thing. You never know where a good idea may come from. It's like, even Stephen Wolfram's like, oh God, going on 15 years ago now, he was giving like a TED talk or something. He's talking about the physics project and looking for a fundamental theory of physics. And he's basically explaining, it's like, well, I've happened to have built a tech company, and as a CEO that has gathered up some resources, I'm able to do certain things, and perhaps I'm just crazy. But he's like, well, we'll see. He's apparently he was hanging around the dorms till like 4 o'clock in the morning or something. I went home to like cling to my bed and sleep for 10 hours just so I could get here decently early and start doing this. All right. So back to action. Hold on. I need some music going on here. I'm sorry. Otherwise I'll lose myself. Let's go to my standard computational stuff. Hold on. Let me say hi to Punkwaddle. I like Punk Waddle. He's a very realistic, logical penguin. Yes, I'm working on a physics project and visiting my penguin puppet friend. Why? Because we can. Let's wave at everybody. I'm sorry, I know you guys can't hear. Here, well... Here, let's get some wisdom from a penguin. Let's
Sometimes we're in the process, right? We're working on something, whether it's writing a song, writing a book, trying to develop a character, or some sort of thing, and we haven't quite nailed it down yet, but we kind of want some feedback, and I think sometimes when we're not quite ready to give it out to the world, but we know we need some sort of interaction and feedback, you know, either sometimes we show our work to people that
sniping.
maybe we weren't ready for their feedback, or, you know, maybe we weren't really ready to show the idea yet, right? Because sometimes
all of us could be a little bit more like Punk Waddle.
Sometimes creating something, especially if you're in the early stages of being a creator, sometimes it's hard to not take it personally when...
Oh, David, I was talking my roommate, Kiran. He was telling me it literally took him at least a year or two to read through NK. When Steven says that's a big book, I remember I was interviewing him, I reached over, it almost knocked me over. The thing is like it's like I think 2 to 3 kilograms. It's if you need to defend yourself, you don't have a rock. If you've got NKS, you might. F equals MA, man. F equals MA. So, all right, let's continue.
You've poured your heart and your soul into something, and it turns out that it's not well received, or it's, you know, compared to what you were trying to do, it isn't quite there yet, right? And sometimes that can feel soul crushing, right? Whether it's something somebody else said, or you just, you know, look at your final product or your demo product, and then realize it's time to go back to the drawing board, right? I mean, we've all had those moments. And I think therein lies the whole thing, right? Because I know I've talked about a bit that some of us are creators and some of us just have the drive to create something, whether it's, you know, writing something down, whether, like I said, a story, a short story, a song, you know, some sort of way to convey things, right? And then some of us are more, you know, maybe musically inclined, and we want to compose, right? Compose good music. Or maybe you're more crafty and you want to create something, or maybe you want to create an instrument, like, you know, design a new guitar, or, you know, that sort of thing. There's a lot of branches of the creative expression, right? Of creative art, performance art, you know. If you're like me and you want to pineapple and ham it up, right? Yeah, because Hawaiian pizza is delicious. And I'm not also... I don't have to say that because, you know, I had some cousins who were extras in that movie, Surf's Up, right? But, I mean, I just think all around it's a great thing. So that's my plug for ham and pineapple on pizza. There, I said it.
Oh, there we go.
Going back to it all, right? There's this whole sort of... When you put your heart and soul into your craft, you want it to be well received, right? Now, for a side note, there's a lot of people that say they aren't artsy, but they're very creative, have a really crafty imagination.
Oh,
and,
atheists.
you know, sometimes those people aren't necessarily creating something new, but they're problem solving things in ways, right? Or in math and science. And
it might be a little while, because there's a list of things I need to go through, and some of them they're all so fascinating And again, I kind of have limited time. I kind of get that I'm literally procrastinating in the middle of a project while I'm supposed to be streaming, working on the project, while listening to my penguin friend, and he's all right, cool, thank you. I'm just the penguin's talking about math and science. Let's continue.
Taking what they know and applying it in different aspects or ways that's not conventionally applied, and realize certain things translate in ways, or come up with new formulas to translate things, and well, get
Oh my
things
god,
done.
he knows what
right?
we're doing right now.
So I don't want to hear that none of this about, I'm too of a math science brain to be, creative or artistic or imaginative. Right? We're all born with something similar. How it manifests is just kind of depends on our drive and what we're trying to do and our personalities, right? So there, all you guys out there, you got something you're good at, right? And if you haven't figured it out or feel like it's not that good, well, don't be too discouraged, because it takes time, and sometimes we're barking up the wrong tree because we want to do something so desperately. Sometimes
So logical.
it just takes a little time for it to click, right? I mean, most of the greats, they weren't just so naturally gifted that they didn't encounter any setbacks or any failures, right? So, take that with some stride, or some waddle, if you will. So, that being said, the whole being creative thing, right? It's just, I don't know. It's important to keep in mind that, well, when we create something, it like I said, and I've said before, it creates a life of its own, right? And if we're trying to create something for the people around us, or the betterment, or, if it's sort of a reaction or response, which I think a lot of art is, right? A lot of stories, a lot of, whether it be long form or, book series based on things that were inspired, and, that we want to share a world that's in response to our own experiences, right? Or maybe it's just a song that describes a moment that we didn't know exactly how to put into normal words, but there was music and a feeling, and we could share that with the world around us, and so many people are like, oh, somebody gets me, somebody understands, I feel heard, seen, right? Because the human and puppet experience is very, well, there's a lot of things that resonate with a lot of us, because there's there's not a lot of difference when it comes down to it about the emotions and the processing, and we all have fine-tuned nuances, right? And not everybody's gonna get everything, but that goes into honing your craft and figuring out who your target audience is. And sometimes your target audience isn't quite who you thought it was going to be or who you wanted it to be, right? And that takes time to process and figure out. But like I said, there's people out there that, if they're not creating, if they're not being imaginative, right, they kind of feel like there's something missing and something lost. And then I also want to say, like, there's people that are trying to create something new out of, somewhere out of thin air, right? Well, not really thin air, but their inspirations and reacting and trying to create something new.
He's good.
And then there are
saying,
the tinkerers and the makers.
He's not invoking,
really
like,
want to,
well, there
actually,
exists a vacuum, but there's nothing
hone
in
their
it.
craft,
Well,
because
even
they're
though there's
crafty
some
people.
fluctuations there,
So
we're hand waving.
And they know how to make things well, and they, they learn the forms and the art forms of creating, like woodwork or welding.
It gave me the time to figure out what the heck that thingy meant. Okay. So this M is actually the molar constant. Why? Because, well, that's what a big M means. All right, so if we do molar constant. What? Or is it just molar? Hold on. Millimoles. that there, move that there. I mean, I'm I'm still I'm still trying to figure this out. This hold on. All right. I'm sorry. I'm sorry. I'm still listening to him in the background. I probably should just share. I'm try to. There's our. Okay. Let's see. Resets. I'm sorry. I'm just trying to go through finding. Oh God! Did it not save? Oh, this is getting very annoying. Hold on. Let me see. Recents today. I think it's this one. Why does it save it in so many weird things? Nope, not that one. File, open. Let me see. Did it really not save? I mean, most of that was just going through and just listing the thermodynamic stuff. Oh, this is annoying. Oh, no, no, no. I did it over here. Okay, all right, all right. Okay. Okay, temperature just goes really, really. Okay, that's what I did. I just put it over here. All right. So let's just move these guys over here. Sorry, I was putting in my source notes. I was about to lose my mind for a second there. Hold on. Edit. Undo. There we go. Okay, all right. Save. I'm sorry, I'm not even sharing my screen. I'm so terrible. I'm just sitting here, like, listening to my penguin friend while I'm supposed to be doing this. Alright, let's share the entire screen. Alright. Back over here. My apologies. Yep. I need to get 2 screens. I've been living. Even Lorena Creole has told me it's. I mean, Steven, I think, has. Professor Wolf has got like 3 screens, or I don't even know how many. I think he showed it once. Okay, temperature is a very interesting thing, but now we're defined by Boltzmann's constant. All right. Okay, so first of all, save early. I'll save to cloud again. Oh god, that was terrifying. All right. Replace. Okay, and what we're gonna do is we're gonna save another one because this is our second session, so we're gonna do save as. Okay, here's what happens. I go to save as and it just creates the random. All right. Wolfram Units project. All right, so we'll at WSS Units project. All right. Save as WSS Units project 6/28/25. This is 2 because this is our second session today. File save as. Hold on, no. Save to cloud. Okay, I'm sorry. I'm sorry, the stress that just caused, I think I might need to go out and get another nicotine fix. So don't worry, I'm going to keep doing this throughout the day. It's rather than 3 sessions, we might have 4 or 5 just because I'm going to take breaks in between, nicotine up, get food, get caffeine, and all right, so save this to the cloud. I mean, here's the thing. It's like if you have another screen, now you can keep track of stuff there. You can keep track of stuff here. I mean, heck, I guess. Oh, hey, Dan. I know. Speak of the devil and he shall appear. I'm just kidding. Dan is one of the nicest guys I know. Oh, God. It was so great seeing you in Portugal, man. That was a heck of a time. Oh, crap. The penguin finished and I forgot to say bye. Oh, well. So, okay, I'm going to like that thingy for Punkwaddle. Okay, so now we're back here. We're finishing our outline, and then I'll go through. Hopefully by the end of the day, I'll have... Okay, hopefully by the end of the next session, I'll have it... Oh, God, I still got to do Thales, Anaxelmander, Galileo, and then the mod... Oh, God. Now I see why people just use ChatGPT for all this stuff. But then again, I'm like... I actually kind of like writing, to be fair. I think it's an art, personally. If anything, I should probably use just ChatGPT to kind of like organize some of the structure. Actually, no, that's... Jonathan Garad's post resonated with me. It's like, oh, I have all these colleagues that are like, oh, look, I can use all these LLMs for this. Like, they can read these things. And Professor Wolfram does say he likes to, rather than reading through a 120-page paper, it's very busy dude. It's like, read this, summarize. And if there's one thing these good LLMs are really good at, is summarizing. Because even like a year and a half ago, one of the earlier versions of ChatGPT, when you could do the transcript plugin, I had to read one of Thad's like hour and a half lectures. And he's like, Thad Roberts claims, blah, blah, blah. He's like utilizing this. It's like when he was saying something that was outside the realm of generally accepted physics, so to speak, it would say, Thad claims, blah, 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 blah. I'm like, oh my God, it's doing news. It's actually reporting. It's not saying, well, this is absurd, this person, blah, blah, blah. It was quite refreshing. So at least for the summarizing, it seems to do a really good job. Okay, Dan, okay. So the current SI thing, Dan, hold on, let's go back. They use the amper. Okay. I'm gonna next week, once I finish this summary, this is my weekend homework that I need to do and start. I'm gonna code something like this, except I'm gonna try to omit the mole and probably the candela. And I'm gonna argue that the ampere should actually be the coulomb. We should be using the coulomb instead. And my two arguments are, number one, given the redefinition, sorry for the potential epilepsy causing shiny things. Okay. So here's the thing. On May 20th, 2019, the ampere is based on the fundamental physical constant, the elementary charge, E, which is the amount of electric charge in a single electron or a proton. Okay, so negative for the electron and positive for the proton, though technically I think it's actually the opposite. Listen, if I was Ben Franklin and I was flying a kite and it gets struck by lightning, I'm just going to say that seems like a negative experience to me. Hence, that's full conjecture and speculation on my part. Okay, my argument is why we should use the coulomb as a fundamental unit is, number one, I've seen Thad literally do magic with it. And again, the five bases, time, space, charge, mass, and temperature. You can basically reproduce the constants of nature. Aside from that, it's all right. Right now, the ampere, the unit of current, is based upon elementary charge, which is in coulombs. It's literally basing a fundamental unit on another unit. That's it. Oh, and then was it Dugan, one of the fellows at the institute? He's like, well, it's like even with like the hypergraphs and everything, it's like, can we try to figure out what like alpha, the fine structure constant, is? And like he said that, I'm just like, okay, because he had seen the shirt, and I'm like, well, to be fair, you need to divide by the dimension of kilograms, which is kind of why I wanted to study units to see if that even makes sense, because that's the main objection, and that's a totally valid objection. It seems like a naive thing to do. My current best argument is, well, if you think the Planck mass means something, to be fair, it's like if you're going to say the kilogram is irrelevant, doesn't mean anything, it's like, well, if the kilogram doesn't mean anything, then this doesn't mean anything because it's expressed in kilograms. So my best argument right now, and again, I'm going to go through the Wolfram methodology because, to be fair, they have some methodology for units, but they haven't really. It was initially done, and they haven't really touched it. And they were just looking for the relationships between different things. And to be fair, if you're able to at least have a generalized model that can kind of replicate the effects of special relativity, you can basically see things that look a lot like black holes and stuff that seems to separate from the graph, or at least be a place where that's undefined. And if basically the correction term for general relativity that you require for your hypergraph is literally the Ricci scalar, the Ricci curvature, that seems like a good thing. But as far as units, they have a general methodology. I jumped ahead, did a quick calculation, and my mind was kind of blown because I'm like, that's not supposed to be there. We'll get to that eventually. But we need to do homework at this point. The other thing is, okay, the reason why I say also charge, or excuse me, the coulomb should be used is because, well, if alpha is a dimensionless thing, so like structure constant. Okay, its definition, official definition is this thingy here. That's elementary charge squared over 4 pi c, the speed of light, epsilon naught, the electric constant, or the permittivity of the vacuum, I believe. Either permittivity or permeability times the elementary unit of action. Okay, this is a dimensionless number. Okay, if this is charge squared, that means this whole dang thing down here must be charge squared. Which charge is it? It's the Planck charge. So that means you can computationally reduce the fine structure constant to elementary charge, or the Planck charge, square the whole thing. Oh, look, you get the same number. Okay. Or you can take its amplitude, and you basically get how Professor Feynman liked to think about it, or AKA the way Thad thinks about it as Ja1, which we would say that if the squared version is the fine structure constant, this would be the amplitude of the fine structure constant, which when you square it will give you the probability, bada boom, bada bing, something, something, quantum mechanics. I'm not going to pretend like I understand that at all. Something, all right, we got a position, we get a momentum, position, momentum, blah, 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 blah. We can change stuff. Okay. All right. Now I'm cooking. This is getting good. That means I need to edit. I'll be back in probably about half an hour. I hold on. Let me save my notebooks one more time, just because it's the stress. The stress. Okay, so let me. Okay, so we save that again. Okay, got that there. All right. So the cool. Okay, so the way that Professor Wolfram explained it to me, Dan, was that we were going over. Where's the other notebook? I think I do have the other notebook. Okay, here we go. So let me bring this up here, make sure. Okay, so let's embiggen this. All right. So he's kind of going through this, and what he was saying is the amper. He was. It's basically the flow of charge. He originally was saying electrons, and then being a good particle physicist, he got himself. He's like, it's a measure of the flow of charged particles. Now, again, when he was going over basically the ampere or the electric current and the candela and stuff like that, I'm like, well, aren't those measures of just like density? And yeah, just a quick like half a second thought. He's like, that might be right. And again, that's why he has folks investigate this stuff, because he's looking for a general thing, get a general understanding, and he's done a lot in his life. So he's like, hey, no, this is work for other folks to do, that you can bring up other folks that maybe can actually publish something, have something on the Wolfram website that might be useful for other folks, and set up for potential future research. I'm not going to be able to do the whole history of everything. And again, it's maybe, I don't know, 5-7 pages of just details. And again, right now, I'm going to go through, I'll have some arguments for why the mole might be kind of sketchy. Because again, like, hold on. So current is basically the number of charged particles moving. It's a very weird thing. Hold on, let me delete that. All right. Go back here. The protons and electrons. Yeah, it's a measure of like the flow of charged particles. So it's like hold on, ampere. So we'll give. Okay, so the corresponding electron weight is 6.2 times. Basically, it has it on this per electrons per second. Now it says it's the measure of movement, but you literally the difference is, and it took me a while because I was adding in meters there. It's literally I think it's ampere times seconds equals 1 coulomb, because to get from 1 coulomb you divide it by seconds. So, but it says charge, moving charge, but coulombs is expressed as something that could technically be stationary, could technically be moving, but then again, isn't it technically always moving because it has some angular momentum or spin or whatever the heck that might be? Okay, and again, that's something for next week to figure out. The mole. No, okay, so the quick rant about the mole is... Okay, hold on. I'm sorry. I gotta go because this is bothering me. Okay, this whole thing, they're going over all this. All right. So maybe. Hold on. I was looking at this because, to be fair, this whole thingy. I'm sorry. To 1 joule second, I'm like, all right. If you just put all these numbers in, fine structure constant squared, mass of the electron, speed of light, 2 Rydberg's constants, without any of that moly stuff, you do get Planck's constant. Okay. But if you're going to put this in, that means if that's a molar constant or whatever it is, and that's Avogadro's constant, to be fair, these, in order for it to be the same thing, Planck's constant, those need to be ones. It seems a little redundant, but it's worse. It's worse, because if you're going to divide the molar constant, or the molar thing, by Avogadro's number, you get this. To be fair, if you actually want it to have it actually makes sense, you kind of need to multiply. Or do I just, should it be the other way? Molar? Okay, I'm just confusing myself now. So molar is referring to a unit. What is that? Amount concentration. By constant. Okay, it gives you reciprocal cubic meters. See, I don't know what's going on there. That seems very weird, and it seems like you're just plugging them in. And now if you can just plug them in and call it like a constant, then why the heck can't I just divide this by kilograms then? Because I don't know. I'm sorry. I'm ranting for another few minutes. And again, the only reason why I kind of even entertain that is just because of this. Oh God, where's the crazy calculation? Basically, when you take the whole, what is it? That crazy calculation for the total mass bank of the universe, you divide it by Avogadro's number, and you get approximately the magnitude of a typical globular cluster. I'm like, oh, wait a second. You mean those like star nurseries that end up generating a whole bunch of stars, and then they'll conglomerate, and then you'll get galaxies and stuff? That is ridiculous. I have no idea if that should even be a thing. But and again, that's from a very human perspective. So okay, I'm gonna stop talking now. I'll be back probably in about 20-30 minutes. Just gonna use the restroom and load up on all my eans. So, all right, I'll catch you guys in a bit. Peace.